my slides. So tell me if you can see them.
Yeah, we are seeing it in presentation mode. Thank you, Charlie.
Great stuff. Thank you. My name's Charlie Mockett from Upstream CFD. We're a partner in the exaFOAM project, and I want to give a presentation today talking about really a focus on scalability. I'll be almost entirely talking about CPU-based CFD and what we call high-fidelity CFD, where you can see a couple of examples of what we mean by that. That's stuff with the turbulence being resolved, or at least some of the turbulence being resolved. And this is work with a lot of my colleagues at Upstream CFD who are listed on the title slide, and there are some other collaborative elements in the presentation. So to introduce the presentation, what I'd like to talk about today is I'd like to convey a few points in this sort of topic space from the perspective of ourselves. We're an innovative small medium enterprise. We specialize in high fidelity CFD for industrial applications, and these give maybe quite a different slant to maybe some other institutions, and so it's inherently subjective, but I hope it's nonetheless interesting. And I want to show some of our work on this topic both inside and outside of the exaFOAM project. I also want to get across the value of high fidelity CFD, and I'm going to give an example of how it can be used to make training data for machine learning approaches. And then we're going to talk about the inherent challenges of HPC for the feasibility of high fidelity CFD. High fidelity is also unfortunately high cost, and showcase some of the efforts going on within the exaFOAM project and beyond to overcome these. The main crux of what I'm talking about is I see quite an exciting opportunity to combine two aspects. One is the relatively new appearance of significant superlinear scalability, with also the availability of HPC in the cloud for CPU-based CFD. And also, of course, nothing is for free. Highlight some of the challenges involved in doing that. And I'd like to do all that in an approachable manner, but still not make any mistakes. And no doubt some of my more technical colleagues in the consortium can correct me if I do make any mistakes, and please do. So when we talk about high fidelity CFD, it's always helpful to look at the spectrum of turbulence modeling approaches. This is an old diagram showing how the different amounts of fidelity and cost can be arranged in a spectrum of increasing computational cost on the one hand and method accuracy on the other hand. On the left-hand side, we have RANS, Reynolds Average and Navier-Stokes methods, where all of the turbulent motion is captured by statistical models, and these have been routine since the 1990s. At the opposite end of the spectrum, we have direct numerical simulation, where every single turbulent eddy is perfectly resolved in time and space, which is hugely costly. And in between, we have a range of approaches such as large eddy simulation and then hybrids of RANS and LES. Examples of which are detached eddy simulation, or maybe wall modeled LES, and SBES being some things you'll probably have heard of. The dates here saying when these technologies will be ready, it's important to note these are from the 1997 paper of Spalat and co-workers, where the DES method was introduced. It's always interesting to review those dates and see where we stand thanks to new advances. So the idea is that these are what we call turbulence resolving approaches, or scale resolving approaches. So we capture the motion of at least some of the turbulent eddies by the grid and the model, the solver and the numerics all working together, and this is inherently costly. The advantages over RANs are more accurate prediction of flows with large-scale separation, and there are also applications where you need to resolve the motion of the turbulent eddies, for example, aeroacoustics, unlock the mechanism of direct simulation of aeroacoustic noise. So that's what we mean when we talk about high-fidelity CFD. And here's an example of a relatively recent simulation. This is a detached eddy simulation of the drive air notchback model, which is a very well-known public domain test case for automotive aerodynamics. This is the case from the Automotive CFD Prediction Workshop series. And yeah, this is an example of OpenFOAM working with advanced DES models, robust and low dissipation solver and numerical schemes. It's also important to say that DES and these kind of methods are widely used in industry today for external aerodynamics because of the essentially, it's on balance, it's seen that the additional cost is worthwhile for the improved reliability. It's always difficult to say what is the computational cost of these, and the mileage varies hugely depending on your specific implementation, the settings that you use, and also how quickly the flow matures and converges statistically. So I don't want to give so much a number, but to say that, to give you a feeling that you're talking about meshes in the order of roughly 100 to 300 million cells, the time step in the region of 10 to the minus 4 seconds, and that you need anything between around 3 seconds to 15 seconds of simulation time, depending on the statistics of the flow. So that should give everyone familiar with CFD an idea for the computational cost of DES. So I'm going to jump into an example, which I won't dwell on too much. This is some recent work that we've been doing to generate a training data set for machine learning. And the background is that, yeah, machine learning, you just have to have a brief glance at LinkedIn, and then it's relatively convincing that the technology has the potential to revolutionize certainly automotive aerodynamics, but also plenty of other fields. And there are surrogate models being deployed today which offer instant feedback on design iterations, or essentially instant, near instant, instead of needing to wait for an overnight CFD run. So it's immediately apparent how much potential is there. Potentially it always brings challenges. Machine learning needs huge amounts of training data, and the reliability of the data determines the reliability of the model which arises from it. So we were involved in a collaborative initiative to generate a large, high fidelity and open source data set. The data set is based on the drive air notchback geometry, specifically the variant provided by Ford, including wind tunnel data that they've provided to validate the workflow. Then the geometry has been parameterized by partners at Siemens Energy and Beta CAE. The geometry variants have been morphed, and an automated and consistent meshing approach has been done using ANSA from Beta CAE. The meshes are around 160 million cells each. We've provided the high-fidelity CFD workflow, which is based on DES and RANs in OpenFOAM. And the simulation has been conducted by AWS on their cloud HPC system, and also the important very large storage for providing these data sets to the public. So there'll be both RANs and DES solutions for a total of 500 cases with morphed geometries, morphed in a systematic way. And the data includes the complete flow field, also the surface data, and then data reduction approaches like slices, and then also aerodynamic relevant post-processing quantities, monitor plots and flow visualization images. So these rather busy animations, which are giving me a slight headache, they show the first 10 runs, just looping to give you an idea of the variation going on. If you're interested in learning more about that, there was a recent presentation given with the slides uploaded to LinkedIn from that link there. So this is the workflow that was used, and as you see, I think the points that I want to emphasize is that it's based on OpenFOAM and an OpenFOAM workflow. The other point I'd like to emphasize in terms of the HPC relevance is that we use scalability data to ensure that every simulation is run at the optimal efficiency. So we have a scalability database for this method and for the platform being used, and then we make sure that for whatever the size of the mesh, we set up the HPC to optimize the efficiency. The other point that I'd like to just touch on is that we control the runtime of every single run individually and automatically using a piece of software called MeanCalc, which we've developed, which essentially tells the simulation when it's mature and can start averaging the flow field, and on the other hand, when the simulation has been run long enough to reach a uniform statistical accuracy target. And yeah, it's important to show the validation of the workflow, and we'll do that using the drive air test case in the variant provided by Ford. There are actually two cases. Case 2A is the baseline case, and case 2B adds additional front wheel air deflectors, which are these red objects in front of the front wheels. So it's a kind of an A/B comparison, which is very important for building trust in CFD methods. And these are the test cases again, which are shared publicly via the Automotive CFD Prediction Workshop. The measurements were carried out in the Pininfarina wind tunnel in a full-scale setup. So I've just picked out 3 bits of data. The first one is the pressure over the roof line, which is always looked at to get an idea of the overall flow topology. Here we see that RANS and DES don't disagree, that they're very close to each other. RANS is giving for this specific thing similarly accurate answers. What we do see is we've got a slight tendency to have less of a separation plateau in these specific runs, but this is a very sensitive part of the car, and different CFD results can vary very widely. Now for an example where RANS and DES are very different, this is a profile of velocity just behind the front wheels, and remember we've got the addition of the front wheel air deflectors. You can see the black dots are the baseline experiment, and the grey dots are the case with the front wheel air deflector, and then the dark blue line and light blue line are the corresponding DES results, and you can see that the effect is being picked up very reliably. Whereas for RANS, the A case is the red line and the B case is the orange line. You can see that that effect isn't being picked up really at all. So it seems as if the flow topology changes very dramatically with the front wheel air deflector in the RANS case. So that's to kind of give a highlight of why the extra fidelity is needed for such investigations. Another example is the side window. It's another important area of the vehicle, and here you can see that the RANS, which actually the red and the orange lines are overlapping, they're significantly further away from the measurement data than the blue DES data is. So let's get onto HPC and talk about superlinear scalability as promised. So I'll start by saying what we thought we knew. This I'm talking about ourselves before the exaFOAM project. So the kind of conventional wisdom was you do a strong scalability test. That means you fix your problem size, and then you increase your number of cores that you're running on, so that you get this kind of plot with on the y-axis, that's your overall time to solution in wall clock time. And then we've got a log-log plot with the number of cores varying on the x-axis. So if we imagine we double the number of cores, we would expect the simulation time to halve if everything goes ideally. And the ideal curve is always the linear scaling given with the dashed line. And for up to a certain point, that sort of works. You halve your simulation time each time you double the number of cores, but at some point, you reach the end of the scalability, the communication overhead starts to dominate, and your performance starts to drop off. The kind of conventional wisdom was that the optimum was in the region of 50,000 to 100,000 grid cells per CPU core. And after that, you start to lose performance. You can speed things up a bit if you go to higher core counts, but you know that you're going to be paying extra. So it's something you only do in a hurry, yeah? And if you've got the additional budget to compensate for the loss of efficiency. And anyway, everyone has, fairly modest still. Most people have fairly modest in-house compute capacities, so there's not so much that we can do with lots of cores anyway. We only have a few hundred cores on our in-house cluster. So that was the kind of the starting position. So imagine, our surprise when we start to see what more modern CPU generations can do. So what starts to happen is you get what's called superlinear scaling. So as you double your number of cores, you start to get a performance increase stronger than the linear expectation. And interestingly, and this is key, this effect holds to much higher core counts than previously before dropping off to sublinear. So instead of 50,000 to 100,000 grid cells per CPU being the optimum, we're finding that something like 8,000 grid cells per CPU core is the new optimum, the efficiency optimum. And you can see, remember this is a log plot, that it is significantly faster in terms of turnaround time than the previous optimum. And this effect has been looked at in much more detail by your host today, Flavio, at the HLRS, and I'd link you to his talk at the OpenFOAM workshop called Understanding Superlinear Speedup in Current HPC Architectures. And one of the key factors is that the trend towards larger on-chip cache in modern CPU architectures. So CFD is the performance is limited by the memory bandwidth, not the processing power. And so the effect that happens is as you use more and more cores, a greater percentage of your overall problem fits in the on-chip cache. And by doing so, you bring the problem closer to the processing and you unlock much more processing performance that's sort of hidden in the CPU. And the effect is so strong that it more than compensates for the communication overhead. So yeah, this is, when you think about it, quite game-changing, really. So this is the question, yeah. You can see this, and the initial results in exaFOAM were for the lid-driven cavity case. It's understandable why people run that. It's a very useful benchmark. But turbulence resolving simulations like LES and DES have a very different, what I call HPC profile. So they're unsteady simulations. They have fine time steps. The field changes very slightly from one time step to the next. And the result is that you have very few linear solver iterations within each time step. And this is especially exacerbated if you're using a segregated solver. So you're not doing very much work each time you go to the linear solver step. You're doing maybe just a handful of iterations and then jumping to the next equation and jumping to the next time step. So it's a very, very different benchmark. So it's an interesting and valid question. can we see superlinear scaling when we have realistic scale resolving cases? So that was the motivation for creating the exaFOAM microbenchmark case MB9, which was a high lift airfoil called the 30P30N, another public domain geometry. We're using wall modeled LES in this case, and there's an unstructured grid of 19.5 million cells, and the link gets you to where you can download the test case. So we have this scale resolving wall modeled LES, and this is the unstructured mesh created with snappy hex mesh using best practices tailored for wall modeled LES. So what we see is that indeed we get the superlinear scaling effect. So the black curves show the same quantity that I showed on my diagrams. So this is the log plot of overall compute time as you increase the number of cores. You're seeing this superlinear effect kicking in. The green lines show then the parallel efficiency going above 1. We're going up to about 1.35 here at the peak. And then this is the important point. This is happening at around 8,000 grid cells per core. So we're indeed seeing, it's not just for the Lid-driven cavity, it's also for, let's say, useful cases in the high-fidelity CFD area. So this gets us very excited. The implications are potentially enormous if this holds for more practical cases. So now we have the combination of the most efficient setup also being much, much faster. If we do a back of an envelope calculation for a typical automotive DES case, we're talking, 160 million grid cells, something like 60,000 core hours. I said earlier I wouldn't say anything about that, but there's a ballpark figure. When we decompose that using the 100,000 cells per core, we end up with 1,600 cores being optimal and a 38-hour turnaround time. If now we can go down to 8,000 cells per core, we can go up to 20,000 cores, and the turnaround time, if everything stays linear, goes down to 3 hours. And then if we factor in the efficiency boost, which is an extra 35%, then we go from 60,000 core hours down to 45,000 core hours, and the turnaround time drops to 2.2 hours. So this is obviously quite sensational, and this is possible today. So what's the catch? Yeah, one obvious catch is, where can I find 20,000 cores? Not in my in-house cluster, but I can using HPC in the cloud. Maybe it's a valid question of whether you could if everybody starts doing this, but currently that's possible. And then, the other thing is, does the effect really apply for massive cases and enormous core counts going beyond that? And decomposing the grid now becomes the new bottleneck of the overall process, and I'll show a few details. Thinking about what the future holds, the trend continues. Chip manufacturers are increasingly adding increasing amounts of cache. Some of them are even sort of sticking it on sideways. They're putting an extra wafer of silicon on top of the chip, which is just cache, and then sort of drilling through to add more. So assuming that they can keep on doing that, this superlinear effect is going to increase to lower core counts. So the benefit will be felt for a reduced number of cores, minimizing maybe these or reducing these downsides. So we wanted to find out where the limit is, and we did this using the high lift HPC Grand Challenge case. So this is a variant of the NASA Common Research Model for high lift. It's test case 2.4 from the ongoing NASA AIAA High Lift Prediction Workshop. The simulations are compressible wall modeled LES simulations using the libwm LES library of Timofey Mucha. We did some validation of that and derived some best practices using the channel flow and the 30P30N case. We generated a templated snappy hex mesh setup for the case where we could vary the problem size. and also tailor the resolution to the flow and to the boundary layer thickness. And the objective was to find basically where's the limit, what's the maximum grid size we can run on today's supercomputers, what's the maximum core count we can reach, and indeed to find out when we find the limit, what causes the limit, so what are the limiting factors. So the outcome was we tested this case on the LUMI C supercomputer. We managed to get up to a mesh of 4.4 billion cells, and we managed to run on a maximum of 65,000 compute cores. The limiting factor, as I mentioned earlier, was the domain decomposition step. We found that the domain decomposition stage exceeded the Q limit when we got to higher core counts. What we also found was that more advanced approaches like Scotch and Car-hip failed when we got to large mesh sizes and core counts, and so we had to unfortunately use the rather basic hierarchical method. As I'll mention again later, a viable solution to this problem has been developed within the exaFOAM consortium known as the coherent mesh representation, and for more details see Gregor Weiss's presentation later today. One thing that we did manage to squeeze out was to use a new approach in OpenFOAM called multi-level decomposition. So we use 3 levels of decomposition by the number of nodes, by the number of CPUs per node, and by the number of cores per CPU. And as you can see from this graph, which shows the MPI calls between the 256 nodes used, doing so significantly reduces the amount of communication. And then the effect is that when we're on, in this case, this is the mesh of 1.6 billion cells running on 32,000 cores, the effect of the multi-level decomposition brings us into, although it's only a mild case, brings us into the superlinear range from being sublinear. So we do see a benefit of this approach, and we can measure the effect. Another performance bottleneck is rotating wheels. I'm going to speed up a little bit. This is another exaFOAM industrial application benchmark case in this case. Capturing rotating wheels is very important for the overall aerodynamics, but having a rotating mesh domain interpolated with the stationary mesh domain introduces a performance overhead and scalability bottlenecks. So this test case, and it's another one where there's a download link, was nominated by Volkswagen, who are exaFOAM stakeholders. And again, it's adapted from the drive air geometry provided by Ford. It's an incompressible DES. And what we've done is we've looked at the effect of developments during the course of the exaFOAM project. So there's been quite a lot of work on different fronts to improve the AMI method and the ACMI method, a non-blocking communication approach, which has been implemented by ESI Open CFD. And you can look at the release notes to get more details. We tested this again on the LUMI supercomputer, and we found that the time to solution improved by a factor of 1.63, so a 63% improvement when we were running on high core counts. So in this case, 4,096 cores. So I'm going to wrap up now. I have one more slide. I hope I've made the case that high-fidelity CFD is a valuable contributor to innovation. And one example of that is where it can play a role in the future is a source of reliable training data for machine learning. HPC has always been a key limiting factor for high-fidelity CFD. Enabling factors are HPC in the cloud, being able to access thousands of cores of the latest generation on demand, particularly for SMEs and startups. This is game-changing. And then I've tried to draw attention to the phenomenon of superlinear scalability, which has potential for breakthroughs in both turnaround time and efficiency. But to harness this requires improvements across the entire workflow, not just looking at the solver. And as mentioned, there'll be a presentation later showing some progress on that front. I hope I've also made it clear that it's important to run benchmarks that have a relevant numerical profile for scale resolving simulations. So not just to run the lid-driven cavity and think that the job's done, and that's why we created a range of scale resolving simulation benchmarks and published them in the exaFOAM project. So I haven't once talked about GPUs, and this is where I do so. So I wanted to make it clear that we shouldn't write off CPUs just yet. So there is a lot of more performance which can be gained from the OpenFOAM you have today, which is fully featured, using modern chips and large core counts. And please, if there are any chip manufacturers listening, please keep adding that cache. It's very, very helpful. However, it's very clear that a high-performance GPU implementation of OpenFOAM will be essential for the future viability of the code. Just a cursory glance at LinkedIn will show an increasing number of proprietary codes which are popping up and demonstrating huge performance and energy efficiency gains. And GPU obviously offers a lot more energy efficiency than CPU-based solutions. So it's also becoming clear that it's not an easy job and that some form of deep integration is required to unlock the true performance potential of GPUs. This is hugely challenging, and I strongly believe that this will require close collaboration from the entire open source and OpenFOAM community. So if you're interested in GPUs, which everybody is, pay attention to Simone Benard's presentation later today. And I'd also direct you to a linked project called exaSIM, which is an ongoing project, and it's a partner project of exaFOAM, where GPUs in OpenFOAM are being looked at. So I'll leave you with the acknowledgement slide, and thank you very much for your attention.
Thank you a lot, Charlie, for your presentation. It was very interesting, covered a lot of different activities.